Day 99 notes, pre-calculus. Today we discuss the properties of logarithms, or at least 4 of the properties of logarithms. We utilize these logarithms we use these properties of logarithms because it again gives us another method to solve for x, an unknown variable. So let's talk about these properties first, and I'll show you how they can be used with real number examples. And if we have time in this video, we'll show a couple examples of solutions as well. So here's our first property. Our first property says that the logarithm with a base a, so logarithm of base a of 1 must be equal to 0. Logarithm base a of 1 must be equal to 0. That's a property of logarithms that just has to be true at all times. And you might ask yourself, well, logarithm base a of 1 equals 0. Why is that going to be helpful for us? Well, we'll talk about that again in just a moment, but imagine, if you would, that we had an unknown number here on this side of the equation, and I somehow had worked the calculation to show logarithm base a of 1 on the left side. I would know immediately that this number on the right has to be 0. Well, how do I know that that's going to be 0? How do I know that the logarithm with any sort of base, any base whatsoever, of 1 must be 0? Well, don't forget that when I rewrite this as an exponent, a must be raised to the 0 power. And what is any a value, any base a raised to the 0 power going to be? Well, that has to be 1. A raised to the 0 power has to be 1. So the explanation, or the reason provided here, reminds us of this exponential rule. Let's take a look at the next property of logarithms. Logarithm base a of a must be equal to 1. Again, a to the first power. What is a to the first power? Well, a to the first power is itself. A to the first power is a. So this property must always be true as well. Logarithm base a of a must be equal to 1. And we know that because of this description here. We must raise a to the power of 1 to get the number a. Property 3. Logarithm base a of a raised to the x power is equal to x. Now here's where it starts to test your mathematical brain a little bit. Let's see if you can recognize the rule for this. Don't forget that this logarithm base a must be raised to this power x, and we're trying to make that equation equal to the expression a to the x. So let me write this over here and see if it makes a little bit of sense to you. Logarithm base a of a to the x must be equal to x. So since that logarithm is equal to x, I know that a raised to the power of x has to equal our target. Our target was simply a to the x. So what power is it that we must raise a to in order to equal a to the x? Well, that power has to be x itself. So logarithm base a of a to the x is equal to x. This one is a particularly powerful property that we will use many, many times over as we get into more complicated logarithmic equations. You'll definitely see that one again. This next property is really just an extension of the definition of what a logarithm is. I'm going to rewrite this as a to the y power equals x. This is how our property, or how our logarithm, was introduced to us in the first place. A to the y power is equal to x. Now, we learned immediately yesterday that I could rewrite any exponential function as a logarithm. So logarithm with a base of a of x must be equal to y. And again, we know this. A raised to the y power is equal to x. A raised to the y power is equal to x. And this is how I can rewrite it as a logarithm. Now notice with these definitions that y has been solved for. Y is a variable now by itself. So I can use a substitution property and replace this y over here with what we said y was equivalent to over here on the right. And so this is where this statement comes into play on the left. A, now instead of being raised to the y power, we're raising it to what y is equivalent to. Y is equivalent to logarithm base A of x. We know that that is equal to x. So again, I made this substitution. I put this logarithm base A of x in place of y. These two are equal to one another. So I've just simply made that replacement, and that's what supports our statement here. Additionally, when we look back at our definition, this was one of the final statements that we made about logarithms. The logarithm base A of x is the power to which A must be raised to get x. Let's see an example of each of these properties using some numeric values. In this problem, I have logarithm base 5 of 1, and that equals x. It would be just the same as if I asked you to evaluate logarithm base 5 of 1. Your job is to find out what x is. Your job is to find out what the solution to logarithm base 5 of 1 is. Well, you should recognize that the logarithm base anything of 1 is equal to 0. This is that first property that we talked about. Anytime we take the logarithm with a base of a number 1, the result has to be 0. 5 raised to the 0 power would equal 1. X has to be 0. Look at property number 2, logarithm base 5 of 5. The base and this target match. 5 and 5 match. 5 to the what power equals 5? Well, that power has to be 1. 5 to the first power is equal to 5. That's property number 2 in action. Property number 3, if I have logarithm base 5 of 5 raised to the 8th power, what does x have to be? Immediately, without doing any math, you should recognize that x has to be the 8th power. 5 to the what power equals 5 to the 8th power? 5 to the what power equals 5 to the 8th power? You should be asking yourself this question. The number has to be 8. You can see that solution without doing any math. In this example, let's think about how we can rewrite this exponential function as a logarithm. Logarithm base 5 of x must be equal to logarithm base 5 of 12. Again, logarithm base 5. So 5 raised to this power, this is the entire, this is the number that replaces the power, must be equal to x. 5 to this power equals x. 5 to this power equals x. Well, if logarithm base 5 of x is equal to logarithm base 5 of 12, what does x have to be? X has to be 12. I'd like to finish out this video with two examples of the properties of logarithms in terms of the geometric sense, what these will look like. And again, remember from the start of this week, we said that logarithms are the inverses of exponential functions. Logarithms are inverses of exponential functions. So what I would like to do is create a table of data points for x and y, and then turn around and plot the function f of x equals 2 to the x power. Now I'm going to use all of the x values from -3 to +3 in increments of 1. So -3, 2, 1, 0, 1, 2, and 3. And I would like to find the result for y, or in this case, since we're using function notation, the result f of x. So I'm going to pause the video here for just a moment, and I encourage you to do the same and calculate your results for 2 to the x power, and we'll fill in the table when we return. And here we go. 2 to the -3rd power is 1/8. 2 to the -2nd power is 1/4, and so on. We have a series of values. Now let's plot them in a graph. when x is equal to -3, we have a y value or a function value of 1/8. That's very close to the x-axis. The value at -2 is 1/4, just slightly higher. At -1, we have a value of 1/2. At 0, we have a value of 1. This is that common point for all basic exponential functions. At 1, we have a value of 2. At 2, we have a value of 4. At 3, we have a value of 8. So we have all of these points establishing the shape of this plot. And if I put it together here, we have a curved line that looks like this. So again, this is our graph of the exponential function. And next we want to take a look at what happens to the graph for its logarithmic function. So let's consider what would the corresponding logarithmic function be and create a table of data for this function and plot it. So again, we would start it with f of x is equal to 2 to the x power. We can rewrite this. We can recreate a logarithmic equation. So logarithm base 2 of x is equal to y, or f of x, I suppose we should use, since we're working with function notation. That's equal to f of x. And I need to be very careful here. It's 2 raised to the x power that equals f of x in our original function. 2 to the x power equals f of x. 2 to the x power equals f of x. So our function notation has to look like this. So keep in mind at this point that these two equations are equivalent to one another. They're the same. This is not the corresponding logarithmic function just yet. This is just us rewriting our exponential function as a logarithm. So when I want the corresponding logarithmic function, when I want its true inverse, let's say, then I want this function, logarithm base 2 of x is equal to f of x. Or better yet, since we're used to writing the function notation at the beginning, f of x must be equal to logarithm base 2 of x. So let's create a series of sample points here and plot those. So x and f of x. We'll pick a few points here and see what this graph then would look like. The problem we have with this, though, is that it's very hard to pick x values and obtain a result. For example, if I chose -1, -2, 0, 1, and 2 for my x values, it's very hard for me to say what is the logarithm base 2 of -2. I have to think, well, 2 to what power equals -2? Again, 2 to this power has to equal x, which we established to be -2. 2 to the f of x power has to equal -2. Again, quite difficult to think of to find that solution. So let me show you a method that we can use to help simplify this a little bit. Instead of picking a value for x, let's pick a value for f of x. Again, we're dealing with f of x equal to the logarithm base 2 of x. If I pick a value for f of x, that will be very easy for me to work, because then I can raise 2 to that power and obtain a result for x. So let's say that we leave f of x equal to -3, -2, -1, 0, 1, 2, and 3, just like we did in that last problem. And you'll start to see that when 2 is raised to the f of x power, that would be equal to x. So 2 raised to the -3rd, well, we've seen that before. That's an eighth. 2 raised to the -2nd power, well, that's 1/4. This is a half. This is 1. This is 2. This is 4. And this is 8. We have the exact same numbers as the table that we saw above, but there's one major difference. This time, the values for x were calculated from the values of f of x, and they've been switched. Instead of an x value of -3 and a y value or function value of 1/8, the roles have been reversed. We now have an x value of an eighth and an f of x value of -3. Can you imagine what that graph might look like? Let's consider this, x with an x value of 1/8. Here's my x value of 1. 1/8 is just to the right of that. It's going to have a function value, or an f of x value, of -3. So over 1/8 down 3. Then we need a x value of 1/4 with a function value of -2. So over just a little bit more, but we're down 2 units. X value of 1/2, a y value or function value of -1. X value of 1, function value of 0. X value of 2, function value of 1. X value of 4, so here's 2, there's 3, there's 4. Function value of 2, and an x value of 8. Let's make some room here. 1, 2, 3, 4, 5, 6, 7, 8. Function value of 3. Take a look at this shape. Looks something like this. How does the shape of this logarithmic graph compare to the shape of this exponential graph? They are inverses. So again, they're inverses based on our calculations, and now we see that they are inverses based on our drawings, based on our graphic representations. If I put the exponential function down here as well, so we have the point 0, 1, we have the point 1, 2, we have the point 2, 4, we have the point 3, 8, so 4, 5, 6, 7, 8. Okay, and then we go left 1 unit, and we're down a half to a fourth to an eighth. This graph looks something like this. And a telltale sign by looking at graphs that lets us know that we're dealing with inverses is if these two are mirror images or reflections of one another over the line y equals x. And that appears to be what we have here. Over 1 up 1, over 2 up 2, over 3 up 3, over 4 up 4, etc., etc., etc. We're dealing with the inverse graph. So we started this video with the algebraic properties of logarithms, and we finished up looking at some of the geometric properties of logarithms. And this is a really important one to notice. The graph of an exponential is the inverse of the graph of the logarithm. That's yet one more way to show that these two are inverses of one another. Keep working on the practice exercises that I've pointed out to you, and be sure to ask questions tomorrow in class. We're preparing for the quiz on Friday, so tomorrow will be an opportunity to ask for help again and to look at some of the review questions as we get ready for the quiz on Friday.